Hey guys, today we are going to learn about physics informed neural network, abbreviated as PINs. So, neural networks are function approximators. What do I mean by that? So, what neural network tries to do is it tries to create a function. It tries to generalize and create or frame a function which maps the input to the output accurately. So all these complex structure, all these complex neural networks are at the end of the day function approximators. Alright. So why is it called pins? General or normal neural networks do not have the knowledge of physics. They are not governed by the rules of physics. So and in several conditions and in several domains such as aerospace engineering, we will want to have a robust model which does have the laws of physics, does have the knowledge of the laws of physics and are governed by the rules of physics. So what we will try to do is we will try to imbibe the laws of physics into a neural network, and we'll try to encode physical equations and constraints into it. So now we'll be trying in this lecture we'll be trying to solve ordinary differential equations with the pins. For that we'll be utilizing partial derivatives. As you all might know, partial derivatives are an important part of any neural networks. These are used in the back propagation process. Alright, and we'll be using automatic differentiation system like autograd and gradient tip. So autograd is available in PyTorch and gradient tip is available in the TensorFlow, and these are used for differentiation and partial differentiation purposes. So we'll try to create a loss function using the ordinary differential equation, and we'll try to minimize it, and we'll see that voila, it solves the ordinary differential equations. Alright, so we'll be trying to first solve an ordinary differential equation of order 1. This is the equation we'll try to solve, and this is the condition that is given. So dy by dx equals to 2x plus 1. Alright, if we try to solve this using conventional methods, what we will do is we'll use variable separable method and take dx to this side and integrate it, and this is what we'll get, right? Y equals to x square plus x plus any constant c, and if we put this condition in this, we will get the solution as y equals to x square plus x, and this is the graph that we will get. So now if our model also predicts a graph like this, we will know that it has learned the solution. Okay, so now we'll try to frame the loss function. What we will try to do is we will use what we have. You have to understand that this is not we have, right? This is we have got this equation from conventional methods, right? These two are the things that we have at our hand. So we will use this and create a loss function, and we'll try to minimize the loss function so that our model learns about this. Our model learns about the correlation between the y and the x, and in turns it learns about the solution of it. So what we will do is in this equation, in this differential equation, we will take everything to the LHS. So dy by dx minus 2x minus 1 equals to 0, right? And we will try to minimize that, and also we'll use this constraint that we have. Alright, and we'll try to minimize it in the loss function. So so if our model successfully minimizes this, we should be getting something like this. We should be getting a solution like this, and this is the graph that we will be getting. Alright, so this is the loss function. As I have already told you, after getting everything on the LHS, dy by dx minus 2x minus 1, will first take a square of it and then take a mean of it. So this will be like an RMS loss. Alright, and this is the constraint we have, y0 minus 0 square. Now this 0 here is irrelevant, but I have still written here for your understanding, because if it were y0 equals to 5, right? Then you will have to write that y0 minus 5 square. Okay, so yeah, this is the loss function that we'll be using, and we'll try to minimize this loss and get the solution of the differential equation. Okay, now let's jump into the code. So here we're importing torch, and this is the model that we'll be using. This is the neural network. Okay, so it has 3 layers, and we are using sigmoid activation functions for it. All right, so here we are using an instance of the model. This is the loss function. This is one of the most important part of any pin. Okay, defining the loss function. So here we are getting the x, and this is the x we have. Now we'll be passing the x through our model, and we'll be getting the prediction, which is the y. Now we will use torch.autograd.grad function to get the differentiation of y with respect to x. So we'll be getting dy by dx. Now you will have to mention create graph equals to true if you want some further differentiation. If you want maybe the second derivative of this, then this will be quite helpful. So yeah, try to keep this as true. And this is the loss function that I have already discussed here. All right, this. So yeah, we are taking the mean square of dy by dx minus 2x minus 1, which I have already discussed here. And yeah, so what this does is it first creates a tensor of value 0. Okay, and then unsqueezes it, and what unsqueeze does is it creates a batch of 1, right? And then I'll be passing it through the neural network. So this will just basically be y of 0. All right, for the value of 0, for value of x equals to 0, we are getting the value of y. So this is basically it, minus 0. Now this is also irrelevant, but still I have written it for your understanding, and then I'll be squaring it and summing this thing. So this code right here, this line right here signifies this loss function, this loss. All right, so this is the data point. Okay, we'll be using 1000 data point from -2 to 2, and the optimizer we'll be using is lbfgs. Okay, and this function we'll be using in the optimizer step. We'll be passing through the optimizer step this function, and we'll be running the epoch for 20 times, and after that we'll be using matplotlib for getting the predicted versus the exact. So as I have already discussed here, this is the solution we got from the conventional methods, right? Y equals to x square plus x. So I'll be using that for the exact plot, right? And again, we have got x here, and we'll be passing it through the neural network to get the prediction, and this is the predicted graph. So as you can see, this is the predicted is in blue and exact is in orange. As you can see, they have coincided well. So congratulations, you have solved your first differential equation using neural network. All right, so now let's go and do something more. So yeah, we'll be solving ordinary differential equations of order of 2. So yeah, this is the equation that we will be solving. D square y by dx square minus 3 dy dx plus 2y equals to 0, and these are the conditions we have. Y0 equals to 4 and dy dx 0 equals to 5. So now if we solve it using conventional methods, you should get a solution something like this, and plotting it in Desmos gives us a graph like this. So if our model also learns well, it should give us a graph like this. All right, so I have already told you about the loss function, right? How we will create the loss function. I urge you to pause this video for a bit and try to frame the loss function for this equation. All right, okay, I hope you tried it. Okay, so the loss function for this equation will be something like, we already have everything on the LHS, right? So we'll be using that and taking the RMS of it, and we'll be using these conditions y0 minus 4 and dy by dx 0 minus 5. We'll be using this condition to frame the loss function. So this is the loss function, and this is the equation we have here, and we're taking the square and then the mean, and these two are the conditions, y0 minus 4 and dy dx 0 minus 5. Alright, now let's look at the code of this ordinary differential equation of second order. So yeah, here we are defining the network again, and yeah, here we are using an instance of this network. So this is the most important part, the loss function. So we have got the x here, okay. So and we have got the y here. Y is the prediction of our neural network. So yeah, we'll be using AutoGrad again to get dy dx, which is a differentiation of y with respect to x. Now try to now we'll have to keep the create graph equals to true, because in this specifically in this code, in this equation, we have the second derivative, right? So we'll create the second derivative here, which is dy by d square y by dx square, which will be the differentiation of dy dx with respect to x. Okay, so yeah, you can see the parameters here. Okay, so now we have got x, y, dy dx, d square y by dx square. So now we'll try to frame the loss function, which is something like loss function, um, which gives us a loss of something like this. So yeah, we have framed it here successfully. D square y by dx square minus 3 dy dx plus 2y. We are taking the square of it and then taking the mean of it. Then these two are the conditions here. Y00 just gives us, yeah, y0 minus 4. Alright, y00 minus 4 square, and this is the second constraint we have, dy dx 0 minus 5. Alright, so yeah, we have also got the loss function here, and this is where we are defining the data points. We are taking 100 point from 0 to 2. The graph will be also from 0 to 2. Okay, so yeah, this is the optimizer we'll be using, the same thing, and we'll be running epochs for 20. And after running that, this is the we are also getting another set of data points and another set of predictions, which we'll be using for plotting the predicted graph. And then this is this thing, this torch.exp, this thing is the solution we got through conventional terms, which I described here. Okay, so yx equals to e to the power 2x plus 3 to the power x. This is the thing I have defined here. This will be the exact. So now the graph looks something like this. So this is the predicted is also in blue and the exact is in orange. As you can see, they have coincided. So you have also successfully found the solution for ordinary differential equation of second order. So yeah, congratulations. So now guys, I'll be ending the video here. If you have any suggestions for me for further videos, or if you want the code, just let me know in the comments below. And yeah, peace out, thanks.